So just before I start talking about what quicksort is, I just want to say that unlike the other sorts we've been talking about, there's a lot of different little nuances that you can do differently. So depending on what website you go to or what textbook you read, things are going to be a little bit different. They follow the same general idea. So just keep that in mind. And like when you're doing the homework, it's probably what you see in Zybooks. I think they cover quicksort in Zybooks, but it may not be the same thing exactly that I'm showing you. So for just to be consistent, stick with what I'm showing you. Okay. General idea is we're going to pick one of these numbers to be a pivot. We're going to move all of the numbers less than the pivot to the left of that number or to the beginning of the array. And we're going to move all of the numbers greater than that pivot to the end of the array. Then what we're going to do is, and then the pivot's going to be in the middle, right? So then we know all of the numbers less than the pivot are on the left, all of the numbers bigger than the pivot are on the right. So now I just do that same thing again recursively with the left half and the right half. Okay. Downside to that compared to merge sort is that we don't have any way of ensuring that we're going to get the list something close to being cut in half, right? We're just going to pick a pivot. If it turns out that the pivot we picked is the smallest number in the array, then we didn't gain very much. So worst case scenario, quicksort can actually turn out to be n squared if you just keep picking a pivot that is just at the very end of the array. But that's sort of unlikely, right? And in general, if you just pick random numbers, quicksort is going to be faster than merge sort. The advantage is that you're doing everything very quickly each time through. Okay. So one of the big questions about quicksort is how to pick the pivot. In an ideal world, what do we want the pivot to be?
Whatever's middle, in the middle, like middle number.
The middle number, there's a name for that in math.
Median?
The median, yes, right? Ideally, we would like to pick the median to be the pivot so that we split the list exactly in half every time. But in order to find the median, we would have to do a big O of n operation, look at every element in the array. So that would sort of ruin things. So we just have to do our best. Sometimes there's a strategy of picking a number towards the beginning, picking a number from the middle, picking a number from the end, taking the median of those three numbers and using that. I guess the idea there is in case they're already in some semblance of being sort of sorted. What we're going to do is just keep it super simple. We are going to choose the last item in the array as the pivot. So in the end, we're going to take that pivot and we're going to move it towards the middle so that all the numbers less than it are on one side and all the numbers greater than it are on the other side. So you'll see how that comes out. Okay, so I need to actually, on this one, I need to actually get the code up here so I make sure I'm doing it right. Don't want to. No, I'm not going to show you the code yet. By the way, just as a quick digression, when I originally wrote the quicksort code that you will see in the lesson or in a link from the lesson, I spent like a day on it. And I was using quicksort code that I found in different places online, different textbooks, and I could break all of them. If I tested it thoroughly enough with enough different sequences of random numbers, all of them had some sort of bug in them. So haven't been able to break mine yet. I'm pretty confident about it. but we'll see. I guess I'm just saying that to say, it's a pretty hard algorithm to get exactly right. So we have to be really careful. A lot of it had to do with like if there were duplicate numbers, it would break or something like that. But okay, so we're going to pick 60 as the pivot. And so the way this works is we start with, I'm going to do the same thing again. I'm going to call this a pointer, even though it's really an index. Okay, we're going to start with a pointer to at the left end of the array and a pointer at the right end of the array. I'm going to compare those two. I'm going to move L up until I find a number that is greater than the pivot. Because it shouldn't be that, it should be at the other end of the array, right? I'm going to move R down until I find a number that's less than the pivot, because it should be at the other end of the array that way. So looks like I've already found that. So actually, let me. Okay, so first thing I'm going to do is swap the 43 and the 82. That makes sense? Found a number bigger than the pivot at the left end of the array, found a number less than the pivot on the right end of the array, so I'm going to swap them. So the 82 becomes 43, 43 becomes 82. Then I keep going. I'm going to move R down until I find a number less than the pivot. So that actually turns out to be the 35. I'm going to move L up until I get to a number that's greater than the pivot. That's going to put me at the 92. Swap those two. 92 and 35. Oh. Okay, keep going. Move L up until I get to a number that is greater than the pivot. That's just going to be right here. Move R down till I get to a number that is less than the pivot. It's going to be right there. Swap the 53 and the 67. And I keep doing this until what? They cross, yeah. Cross or touch, something like that. Okay, so move left up until I find a number greater than the pivot. Move R down till I find a number less than the pivot. Swap those two. 90, 38. Okay, whoa, I did something. 15, thank you. No. That look good? Okay. Move L up until I get to a number greater than the pivot, or I meet R. So L is going to move up to here. When they meet like that, I'm done with that part of the algorithm. Okay, I don't even try to move R. R is already, I just stop that part of the algorithm. Next step is, okay, here's the part. Here's what the code says. If L no, sorry, I'm at the wrong place. If L is greater than the pivot, swap L into the pivot. Okay. The reason that I have to have that if L is greater than the pivot is that in very, very rare situations, if you leave that if statement out, it'll do the wrong thing. I think we might get to see an example of that, but I'm swapping L into the pivot. Okay, so now here's the pivot. Okay, so now I just do that same thing with both halves. So let's look at this left list. We're going to choose 38 as the, well, so let me start by. So by the way, this is something I should have said a long time ago, but I kept forgetting. You get that what's happening here is I'm just drawing a picture of the array at different points in time, right? Snapshots of the array after each pass through the array. So see the pivot in the beginning because of the right. Yes, that is correct, Paula. I chose 60 as the pivot because the way that we decided to do it is we're just going to take the last item in the array as the pivot. Lots of different ways of choosing the pivot. That's just what we decided to do. Okay, so 38 is going to be the pivot for this list here. Start L there, start R there, move L up until I get to a number that is greater than the pivot, or I meet R. So this is one of those cases where the number that the pivot is no, it's 38, never mind. Okay, so L is already at a number greater than the pivot. The pivot's 38, right? L is already at a number that's greater than the pivot. R is already at a number that's less than the pivot. So I swap the 43 and the 15. Move L up until I get to a number that's greater than the pivot. Move R down until I get to a number that's less than the pivot. Swap L and R. Move L up until I get to a number that's greater than the pivot, or I meet R. Done with my swapping. Now I just have to do that final last little step. If L is greater than the pivot, swap them. It is, right? 30. So I'm going to swap the 38 and the 55. Okay. And then circle the pivot. Okay, so now I've got this sublist here on the left. I've got it split up into two lists. One, all of the numbers are less than 38. The other one, all the numbers are bigger than 38. Okay. Let's do the same thing on the right side. So the pivot's going to be 90. Start L at the bottom, start R at the right. Move L up until I get to a number that is greater than the pivot. So that's going to put it right there. Move R down until I get to a number that is less than the pivot. I'm already at a number that is less than the pivot. So I'm going to swap the 82 and the 96. Move L up until I get to a number that is greater than the pivot. Move R down until I get to a number that is less than the pivot, or I meet L. And technically, I should say that, or I meet the other one every time, right? So there's where we meet. So now I'm done swapping. Now I say, okay, if L is greater than the pivot, swap them. And there's our pivot on that side. Okay. In real life, in a quicksort, what you're going to do is you're going to go down until the list is there have been studies done that have you can do studies to determine what the best point is at which you stop doing the recursion and you just sort the rest using insertion sort or something. I think it's like 8 or something like that. Might be bigger, but we're going to just keep going. Okay. So, and actually applying quicksort to these little tiny lists actually is a pretty good way of checking to make sure that you really get what to do in every boundary case, because there's going to be some weird situations that come up. But if so, I'm going to put L here. I'm going to put R here. And this just tests. I'm testing myself to make sure that I really know what the steps are and I can just follow them literally. So move L up until I get to a number. Wait, so the pivot's going to be the 35, right? So I put the R in the wrong place. Right? If the pivot is 35, then L and R are both going to be on the 15. And so immediately I'm already done with my swapping. And so here's where that if statement comes in. If L is greater than the pivot, swap them. If I hadn't put that if statement in there, I would have swapped those two and got them out of order, right? So they're not, L isn't greater than the pivot, so I'm going to leave it the way it is and mark my pivot. Actually, I should make a copy first. Huh? Copy, paste. Mark my pivot. Okay, let's do this list of 3 now. 55 is going to be the pivot. L is going to be here. R is going to be here on the 43. Move L up until I get to a number greater than the pivot, or I hit R. So done with my swapping. So now I say, okay, if L is greater than the pivot, which was 55, swap them. It's not, so I don't swap them. And 55 is my pivot. Okay, 67 and 82. 82 is the pivot. L and R are both on the 67. L is not greater than the pivot, so I leave them where they are and I mark my pivot. Tracking with me? Sort of.
Yeah, how are you deciding where you're making the pivot each time?
Well, okay, so right here, let's just keep going and I'll be more careful on this one. My list is the 96 and the 92, right?
You're just going left to right to the array. Whenever you find a section that's not so big, you're
Correct.
going the furthest right, non.
Correct. So I've got an array of size 2 here. The right one is going to be the pivot. And then the left one is going to have both L and R pointing at it. And this, in this case, L is bigger than the 92, so I swap them. And 92 is my pivot, right? So I mark my pivot. Okay, now we're all done. These are all size 1, except for this list right here. So let me just finish it up real quick. 53 and 43. 43 is going to be the pivot. L and R both start off pointing at the 53. L is greater than the pivot, so I swap them. And mark my pivot. The marking my pivot part is just so that when I'm grading your work, I can see that you were using the right pivot, right? So it's just for our purposes. It's not really like part of the algorithm or something. All right, so now every single list is size 1 and we're done. And it's sorted, right? Okay, so you may have to watch me do that a few times on the video, or you may have to look at the code. I mean, you can actually follow through and trace the code and do it too. That's what I was doing just now. There was a couple times when I was like, wait, what happens next? So I just look at the code. What do you think about big O on this one? Might have already mentioned this, but so each step here going from one line to the next is going to be big O what?
And
Big O N, right? Each time, each step going from one to the next, I have to look at every single item once or twice to determine whether they need to be swapped or not. So each step takes N. How many steps are there going to be? Well, I'm split. Well, in this is one of those times when I'm going to say, let's talk about the best case scenario. Okay. Not what we normally want to do, but in the typical scenario,
yeah,
you're going to divide your list in half, log in times, right? Just like merge sort, just like binary search. So this is another big O in login sort. Okay, so the question is, could you explain a little why you chose 38 as the pivot here? So the list I was sorting was this list here, the 43 through the 38. And so my rule for choosing the pivot is always just that I'm choosing the last item in the portion of the array that I am sorting to be the pivot. Not sure if that helps or not, but I'm going to go with that for now until I see another question. Okay, where was I going? Let's look at the code. Looks kind of similar to the merge sort, right? I'm just saying, as long as left is less than right. So the base case is left is not less than right, which means it's size 1 or smaller, I suppose. So what I'm going to do is I'm going to choose a pivot, and this is a little confusing, but so the partition is that function is the part where I'm going through and doing all the swapping. And all I'm doing with this is I am returning the index of the pivot so that quicksort knows where the lists start and stop next for the recursive call. So in my case here, I called partition on the original list. And what happens is the partition function makes all of these changes and ends up with this second row. And it returns the index of the 60, 0, 1, 2, 3, 4, 5, 6. So it's going to return 6. So when I make the recursive call, the first array is going from left up to 6 minus 1, 5. And the right half is starting at pivot plus 1 and going up to the right. Okay. So that's all there is to the actual quicksort function. The partition function, as you can imagine, is a little more involved. But not that bad. So the pivot is list of right. That makes sense, right? The last element in the array that we are sorting. Index from right gets 1 less than that. Index from left gets the very leftmost item. And then while index from left is less than index from right, so while the left and right pointers haven't crossed yet, move left up until it gets to a number that's greater than the pivot, or it meets right. Move right down until it gets to a number that's less than the pivot, or it meets left. And then if they are if they haven't met yet, swap them. If L and R aren't pointing at the same thing, swap them. I think there actually may be a situation where you can get these to cross. And so same thing, you don't want to swap them if they just crossed accidentally. I can't remember for sure if that's true, and if it is true, what that situation is, but in any case, we're safe. Right, so as long as index from left, so what one time through this while loop did is it moved L up and moved right down, and then it swapped those two, right? And so we keep doing that as long as they haven't met yet. Once they've met, you saw me do this several times, right? if L is less than the pivot. I mean, I guess I could have just said the word pivot here, right? Then swap them. And return index from left because that's where the pivot ended up. So the question is, so the pivot moves to the median. Then we chose a new pivot on the last index next to our old pivot and move it again to the median of the new array. All of that is correct, except it's not technically the median that we're moving it to, right? We're just moving it someplace where we can guarantee that all of the lower numbers are on the left and all the bigger numbers are on the right. It's not, ideally it would be the median, but we don't know that. But it sounds like that you've got the concept. All right, any questions about quicksort? I did the code, we talked about the analysis. Oh, and it's 420. Yeah, but
I just had a quick question. So it seems that you're moving left before you're moving right, correct?
that's and that's what's happening in the code too, right?
Yeah.
Move left and then move right.
Yeah, that makes sense. Cause I got a little confused about when we first hit when we're moving, the first time we moved L to R and they met each other, I was like, why is it meeting at 90 and not 30?
Got it,
Because
yeah.
Moving left first.
Right.
Okay, yeah.
Okay, yeah, so we move, and that's just, I mean, I could do that the other way around.
Yeah.
But the way our algorithm is set up, we're moving the index from the left first, and then we're moving the index from the right.
Bigger than P or means R.
Right.
Okay.
Yeah. Okay, so if it wasn't 420, I would 422. I would probably just want to play around with the this program that I've been showing you, because we can actually time these. But I think I'm going to just save that for another time. Okay, but I would encourage you to, I mean, it's kind of fun. I would encourage you to go on to the lesson, get that set up and just play around with the numbers a little bit and see how the different sorting algorithms compare. Okay, I'm done. And stuff recording.